Chapter 15 is on acid-base chemistry. How many of you have heard the term acids? Okay. How many of you have heard the term bases? Acids and bases. So. So first I'm going to talk about, there's many different types of acids, but the acids that I'm going to be focusing on is something called a Brunstad acid. Okay, and then something called a Brunstad base. Okay, so a Brunstad acid is something that gives off a proton. So what is a proton? And the way I'm going to teach you a proton is going to be called H+. Okay, H+. Now, some textbooks will call it H3O+. This is called a hydromonium ion, which the way I'm going to teach it to is one and the same. So other professors or other teachers may call it H3O+. Other professors will call it H+. To me, they're one and the same. Okay. So, hydromonium ion. Okay. But the way, just to make it easy for us and easy for the lecture, these are equivalent. So if I talk about H+, what am I really meaning? H3O+. If I'm talking about H3O+, what do I really mean? H+. What do all those two really mean? Okay, proton. Okay, they mean a proton. Okay, so an acid is something that will deliver a proton. So if it's something is very acidic, what will it have a lot of? If something is considered acid or acidic, what will it have a lot of? It'll have a lot of these. Okay, H+. Okay, on the contrast, or in contrast, a Brunstad base abstracts protons or grabs protons or takes protons. Okay. Okay, so it will take a proton. Okay, so anytime you're looking for something that is basic, okay, we're looking for OH minus. Okay, OH minus. Okay, anybody know what this is called? This is called hydroxide. Okay, hydroxide ion. So this would be, anytime you see OH minus, you're looking at something that's very basic or alkaline. Okay, alkaline. OH minus. So giving off a proton. So it takes a proton. All right, so I'm going to give you some formulas here, and you do not have to know how they're derived. Okay, so no derivation. All right, but let me just give you some general formulas. I'm going to derive them for you, but there'll be no derivation on any exam. Okay, so let me give you the general formula for a Brunstad acid. Okay, so we'll call HA the acid. Okay, this is the general formula. This is the acid, any type of acid. Okay, plus H2O. It's going to react with water. This is an equilibrium. Okay, an acid is going to deliver an H+. And then this water takes it and it becomes H3O plus. And this becomes A minus. Okay, this is the generic form. Okay, this, you replace HA with an actual acid. Okay, this will have a Ka. This A stands for acid. Okay, and it's products over reactants. Okay, bless you. Okay, so I'd like for you to memorize this. Okay, this is the general formula. Generic. Okay, you replace this with an actual acid, it will do this. So HA could be any acid. The H2O here is going to be a base. Okay, this base picks up the proton and becomes H3O plus. So this is going to be called the conjugate acid. Okay, to this base. So they're kind of conjugates to each other. And this acid has its conjugate base. What is the conjugate base for this acid, HA? It's this right here. So that would be the generic or general formula for a Bronsted acid. This is what happens when an acid reacts with water. This is what's happening here. Okay, we'll do the same thing for a base. So let us do that now. Okay, I'm going to do the formula for the base. Okay, so this will be A minus. This is going to be the base. The base, it's going to react with water. Okay, this base is going to take a proton, H plus. Okay, and you're going to get HA and OH minus. The OH minus and the OH minus are aqueous. Okay, water is always a liquid. So this will have a Kb. Okay. The Kb is products over reactants. Notice I'm not putting water in here. Why am I not putting water in the equilibrium expression? Because it's a liquid. Okay. So I'd like you to know and memorize this equation for any base. Any base. Okay, in fact, this is the base. Okay, this base takes a proton and becomes HA, and that is what we will call the conjugate acid to this base. Okay, water in this particular scenario is the acid, and OH minus is the conjugate base. So I'd like you to memorize this general formula. You'll replace this with an actual acid. And I'd like you to memorize this formula. You'll replace A minus with an actual base. Okay. What do you see water here? In this first reaction, it's acting like a base. In the sense, it's taking a proton. What about in the second reaction? What is water doing? It giving away a proton, acting like an acid. Okay, so water can be both an acid and a base. Okay, water can be both an acid and a base. Okay, this is called amphoteric. And not something that you need to know unless you want to take, higher level classes, but amphoteric. It can be one of the more amazing properties of water, besides many, is that it can be both acid and a base. In the Bronsted acid equation, it's behaving like a base. In the Bronsted base equation, it's behaving like an acid. Okay. So I'm going to do something now. Again, there will be no derivation on the exam, but maybe you'll learn this a little bit better if I do something and derive something for you. Okay, I'm going to take this equation and this equation. I'm going to add them together. I'm going to add this equation, let's call it equation 1. With this equation, I'm going to call it equation 2. Okay, when I add those two equations, you multiply the equilibrium constants. Do you remember this? Okay, you add two equilibrium equations, you multiply the constants to get the new equilibrium constant. So let's add these. So do you guys see here that this HA cancels out with this HA? Yes or no? Okay. And do you guys see here that this A minus, when I add reaction 1 and 2, cancels out with this A minus? Okay. So adding them together, I'll get one water and another water is 2H2O. This is my sum. I'll get 2H2O. Okay. In an equilibrium with H3O plus OH minus. Okay, this equilibrium we will call KW. And KW is nothing more than, remember, if you add two equilibrium reactions, what do you do to the equilibrium constants? You multiply them. So KW, W stands for water, is equal to Ka times Kb. All right, so at 25 degrees, if you look at your textbook, there is a value for this Kw. So at 25 degrees C, this Kw is 1.00 times 10 to the minus 14. That's the value of this equilibrium constant. That's going to equal to Ka times Kb. So this is the first equation I'd like for you guys to know. Okay? This is the equilibrium value constant of Kw. So this Kw, the magnitude is 1.00 times 10 to the minus 14. It's very, very small. So very little water goes this way. Very little water will go in making H3O plus and OH minus. Okay, very little water will go to the product side. I think I remember reading a book somewhere a long time ago that for every 1 trillion with a T, 1 trillion water molecules, one out of those trillion will go this way and give you H plus acid and OH minus. Okay, so that's how small. Most of the equilibrium is this is in the left. Okay. So that's why your pure water is pure water. Very little is H plus, very little is OH minus. But some is. Some goes and gives you H plus, and some goes this way and gives you OH minus, the base. All right, so we have here 1.00 times 10 to the minus 14, which is Kw, which is equal to Ka times Kb. Ka, let's substitute this value in. H3O plus times A minus divided by HA. Okay, Kb, okay, let's put in this value here, this expression, OH minus HA divided by A minus. Okay, so we multiply them together. We'll multiply these together. Okay, Ka is this equilibrium constant. Kb is that equilibrium constant. Kw is from our textbook. That's what is the equilibrium constant at 25 degrees. So this is products over reactants, 1.00 times 10 to the minus 14. This HA cancels. Okay, it's the same thing, products over reactants. So it's the same thing you get from doing the equilibrium constant here. Okay, remember, water is always a liquid. Okay, water into water is just water. Okay, nothing is dissolved into water. So that's why water is the liquid. It's the solvent. Okay, I'm going to do something to this equation. Okay, I'm going to take the minus log, a negative log of both sides. Okay, not just the log, but the minus log of both sides of the equation. Okay. So this is going to be minus log of 1.00 times 10 to the minus 14 equals minus log of H3O plus, okay, times OH minus. Okay, all that is in products. Okay. So there's no derivation on the exam, but let me just give you some log rules. Okay, log AB is log of A plus log of B. Okay. Log of AB, the product, is log of A plus log of B. But we have the minus sign there, so let me just use this log rule. Minus log of 1.00 times 10 to the minus 14 is minus log of H3O plus, okay, plus a minus log of OH minus, okay, concentration of OH minus. Okay, I'll just put these in parentheses here, okay. So let me tell you something here that you may or may not know. If you take the minus log of anything, minus log, that's the same thing as called power. Okay, so minus log of x is actually p of x. Okay, that p stands for power. Okay, minus log of things. So you can do minus log of my name, and that's p vj, power. Okay, that lowercase p stands for power. Okay, power. Right. Minus log of, I don't know, chair. Okay, is power of the chair. Okay, it's nonsense, but minus log of anything is the power of something, which is lowercase. Okay. So minus log 1.00 times 10 to the minus 14, I'll just do that on my calculator. And what do you get when you do minus log of 1.00 times 10 to the minus 14? Minus log 1.00 times 10 to the minus 14. You'll get 14 equals minus log of h plus. I'm just going to call that pH. Okay, pH, which is the power of H plus. Power of H plus. I'm just, instead of H3O plus, I'll call it H plus. So pH, and then minus log of OH, I'm going to call that POH. Okay. So this is the second equation I'd like for you guys to know. pH plus POH is equal to 14. Okay? This minus the log of anything is the power of that thing. Okay? Minus log x is just power of x. That lowercase p stands for power. Power of H plus. Literally, how strong is it acidic? Power of OH minus. Literally, how powerful is the base? Okay, so 14 is equal to pH plus POH. Okay, so what does pH equal to? What is the formula for pH? Okay, let's go back here. Okay, so what is the formula for pH? We just derived 14 is equal to pH plus POH. But what's the formula for pH? It's minus the log of the H plus concentration. Okay, that's something I'd like for you to know. Okay, what is POH? It's the power of OH. But what do we do when we take the power of something? Okay, we take the minus log. So what's the formula for POH? Minus the log of OH minus the log of the hydroxide ion concentration. So, a couple of things I'd like for you to know. Now, you may have to go back. Okay, can you switch back and forth between these two? So, pH is minus the log of the H plus hydrogen ion concentration. If you want to go back and get the H plus concentration, go back and forth. Okay, it's the anti-log. Anti-log on your calculator is 10 to the power of x. Okay? 10 to the power of x, anti-log. Okay, so you do shift that number. Okay, so the hydrogen ion concentration in moles over liter is 10 to the power of minus pH, and the hydroxide ion concentration, okay, just going back and forth between these two, is 10 to the power of minus POH. Okay. So something I'd like for you guys to know. All right, let's do an ice table. I know people don't like an ice table, but let's just do one here. Okay, we'll do an ice table on this water dissociation equilibrium, whose Kw at 25 degrees from the textbook is 1.00 times 10 to the minus 14. We'll do an ice table here. Okay, water is a liquid, so we don't care because it's a liquid. But let's say some of it goes this way, some of it goes this way. Okay, so initially we'll have 0 and 0. Some of it goes this way. So I'll call it plus x and then plus x. Plus x, plus x. Okay. So at equilibrium, it's going to be x and x for the hydroxide ion concentration and the H plus concentration. Remember, H3O plus and H plus are one and the same, at least the way I'm teaching it to you. Okay, so at equilibrium, we'll have x and x. So let's plug that in to this equilibrium equation. Kw is products over reactants. Okay. Products over reactant, but reactant is liquid, so we ignore it. Kw is 1.00 times 10 to the minus 14. So we'll plug in the values of x and x into our ice table. So x times x is x squared. So x is equal to the square root of 1.00 times 10 to the minus 14. And the square root of 1.00 times 10 to the minus 14 is 1 times 10 to the minus 7 molar. Okay, so what does that 1.00 times 10 to the minus 7 molar symbolize? It's the concentration of H plus, and it's the concentration of OH minus. So at equilibrium, the concentration of H3O plus for this equation is 1.00 times 10 to the minus 7 molar. Okay. So if I take the pH of this, or if I take the negative log of it, which is the same thing as power, which is the same thing as pH, if I take the negative log of the H plus, which is the same thing as H3O plus. Okay, what's negative log of 1.00 times 10 to the minus 7? Okay, it's 7. Okay. So at equilibrium, your pH is going to equal to 7. 7. Okay. At equilibrium also, OH minus is equal to 1.00 times 10 to the minus 7 molar. So let's take the minus log of both sides of the equation. Remember, if you take the minus log, it's the same thing as the power. The minus the log of something is the power of something. Well, the minus log of OH minus hydroxide is the power of hydroxide ion, the POH. And what's the minus log of 1.00 times 10 to the minus 7 on your calculator? It's 7. Okay. So a couple of words about this pH and POH. Number one, it's unitless. You see, anytime you put something in a log, you're not allowed to put units. They don't. Units and log and natural log don't go. So this pH is unitless. Same thing with the POH. Okay. Another thing you may have heard from maybe your biology classes or your other chemistry classes is that this is a scale. Okay, this is a scale. Okay, a logarithmic scale that tells you the power of H plus, the acid in the solution. It's also a logarithmic scale that tells you the power of OH minus in the solution, how basic it is and how acidic it is. So what would neutral pH be? Neutral pH is when the H3O plus is equal to OH minus. And what would that pH be? What would that POH be? 7. Okay, so neutral pH, neutral POH would be 7. What happens if you have more H3O plus than OH minus? Okay, let's say your H3O plus concentration is larger, greater than your OH minus concentration. Okay, what will that mean? Okay. Will that make you more acidic or more basic? It will make you more acidic. What will that make your pH? Higher than 7 or lower than 7? Remember just from beginning class chemistry, it means your pH would be lower than 7. Okay? Because of the minus log rule. Okay? The minus log. So the lower the pH, the more acidic it is. Okay. What happens if your OH concentration is greater, like the opposite? Okay, will that make you acid, acidic, or basic? Okay, basic. What will your pH be? Would it be higher than neutral 7 or lower than neutral 7? Okay, it will be higher than 7. Okay, what will your pOH be if something that's basic? Higher than 7 or lower than 7? What does pH plus pOH must equal to? 14. So if your pH is higher than 7, what will your pOH be if it's basic? It's going to be lower than 7. You see 7, you got to equal 14, right? pH plus pOH must equal 14. If you have something that's acidic, your pH is acidic, but what would your pOH be? Higher than 7 or lower than 7? Remember, they have to sum up to equal what number? Okay, they have to sum up to equal 14. So your pH will be above 7, while your pH is below 7. Okay. Okay, this is the idea behind a scale. Okay, this is a scale. Let's do our pH scale here. Okay, 7 is neutral. We'll do our pOH scale here. Okay, remember, no units. This is all relative. It's no units. So as you said before, if you are acidic, your pH will be below 7. It's no units. Your pH, if it's above 7, will be basic. Okay, if your pH is below 7, you're acidic. If your pOH is below 7, you are basic. Don't get confused here. If your pOH is above 7, then you are acidic, okay? While your pH is basic. These are opposites, okay? Why are they opposites? Because their sum must equal to what number? 14. Okay, this is a scale. And generally in science, the chemistry community and biology community generally go by pH, but you can also go by pOH. Remember, pH plus pOH is equal to 14. All right, one last thing here. Okay, I'm not going to do the derivation for this, but it's the same, along the same lines. One final thing I want to show you. You see this Kw is equal to Ka times Kb. Okay, there's one more equation here. If I take the minus log of both sides, minus log of Kw equals minus log of Kw times Kb. Okay? Okay, minus the log of Kw, which is 1.00 times 10 to the minus 14, is equal to minus log of Kw plus the minus log of Kb, okay, because of the log rules. Okay, minus the log of 1.00 times 10 to the minus 14 is 14. Minus log of Ka, this should be Ka, sorry, Ka. Okay, minus log of Ka is pKa, plus minus log of Kb is pKb, okay? pKb, power of the Ka, power of the Kb. Okay? This is another thing I'd like for you to know. Okay? And just like with pH, pKa is minus the log of your Ka, products over reactants, and your pKb is minus the log of your Kb. Okay, and we can flip back and forth. Okay, your Ka will be the anti-log, 10 to the power of minus pKa, you want to get your Kb, you'll do the anti-log, which is 10 to the power of minus pKb. So another thing I'd like for you to know, the power of your Ka. How good is this acid as an acid? Okay, just like pH, how good is water being, pH is how acidic something is. pKa is how acidic that acid is. Okay, you know, HCl has a higher Ka than acetic acid. Okay, like that. Right, just as also if your pKa is down, just like your pH, your Ka is really high. Okay, just like your H3O plus concentration. Okay, if your pKb is really, really low, that's a very good base because that means the Kb is really high. Okay, it derives from the minus log rules. Okay, how good an acid is, you look for a low pKa or a high Ka. Remember, if you have $1 million, this reaction is moving forward. Okay, same thing with the base. If you have a large Kb, pretend it's 1 million. That Kb reaction at equilibrium is favoring the product side. By the minus log of the power rules in math, that corresponds to a low pKb. A low pKb. All right, so these are the things I'd like for you to know, and that's really the gist of this chapter. All right, let me take the last 8 or so minutes. Let's go over an ice table problem that will be on the exam. So let's get